this series of videos, we're going to be looking at the first major application of acid-base equilibria by studying what we call pH indicators. So for those that don't know, a pH indicator is a chemical that is added to an acidic or basic solution in order to indicate to us, hence the name, whether a neutralization reaction has taken place. Probably the most well-known indicator to secondary school students is a pH indicator that we call phenolphthalein, which is useful because of how radical the color change is. So when phenolphthalein is added to an acidic solution, that being a solution that contains more hydronium than hydroxide and therefore has a pH of less than 7, we see that the indicator does not show up at all, meaning that it is colorless and transparent. However, this changes radically when we put it into basic solutions, because we see here in a solution containing hydroxide that phenolphthalein changes to a deep pink or light purple color, meaning that there has clearly been a chemical reaction here, and the indicator is showing us that. So what exactly is going on with the indicator? Well, we can see that phenolphthalein has a very complicated organic chemical structure. We see that the name phenol within its structure actually corresponds to this functional group here, which is a benzene with an alcohol on it. And this is important in its structure because each of these structures here, each of these phenol groups can actually act as a weak acid. So within a solution that contains hydroxide can use one of its lone pairs to pull a hydrogen off of these phenol groups, breaking this bond and causing it to become a lone pair. However, because of phenolphthalein's unique structure, which is a structure that many pH indicators have, this lone pair can then move down to the oxygen to become a double bond, causing all of the bonds within, or the double bonds rather, within the benzene ring to shuffle around and cause the bond structure to move, leading to a product that has a fundamentally different chemical structure than the original compound did. So the point being that phenolphthalein, like basically every known pH indicator, functions as a weak acid, although some indicators will function as weak bases instead. And when the acid ionization takes place, the structure of the molecule changes very significantly whenever it loses or gains an H+. Now, this entire process is reversible because, again, remember that double bonds can actually move. I wrote the movement of bonds there incorrectly. So, if we wanted to go backward, we could, under the presence of an acidic solution, have the phenol oxygen take back its hydrogen like this and cause the double bond structure to reform back to the original structure here. So the point is that all indicators have reversible acid-base ionization reactions, but because of the radical change that occurs within the structure, each of the different structures formed actually appears as a different color to our eyes. Now, as mentioned, and as we see from the mechanism of ionization from phenolphthalein, all indicators function as either weak acids, as phenolphthalein does, or weak bases, because if phenolphthalein were to take back its hydrogen and go back to its original structure, it would be functioning as a base. And the idea is that these weak acids or bases change structures fairly significantly as they lose or gain H+ ions. Now, because indicators have a very complicated chemical structure, writing out the chemical formula of an indicator is a time-consuming mess that most chemists don't bother with. So instead, pH indicators are usually given the short form of HIND, IND, of course, meaning indicator, and H identifying that the indicator is in its acid form, meaning that it has an easily ionizable hydrogen, and once it loses that hydrogen, we give it the form IND-, indicating that this is the base form because it has a negative charge that is able to take hydrogen from water or from another acid. So in the case of phenolphthalein, the acid form is the colorless form, but the base form is the form that takes on the pink or purple color, and therefore as the pH of the solution increases, meaning that as the concentration of OH- increases, the solution becomes more pink. And the fact that it becomes more pink, the fact that we are seeing more of the base form, indicates that our solution is becoming more basic. And we can see this by taking a look at the actual equilibrium system and analyzing it from the perspective of Le Chatelier's principle. So the pink side is indicated by the fact that we have a higher concentration of the basic form of the indicator. So whenever the concentration of the basic form of the indicator increases, this is due to the equilibrium shifting towards the basic form. Now, how might we do this? Well, we know that whenever the concentration of OH- increases, the solution gets more pink, and we know that OH- is going to react with H3O+, and when OH- and H3O+ react with each other and neutralize to make water, the concentration of H3O+ decreases. Now, when the concentration of H3O+ decreases, we have a situation where our forward reaction rate is greater than the reverse reaction rate, so more of our indicator is able to ionize to the base form, causing the solution to become more pink. So this is why increasing the concentration of OH- shifts the equilibrium to our products and to the basic form of the indicator, because it neutralizes H3O+, therefore causing the rate of our reverse reaction rate to decrease. Now, if we want to reverse the color change, let's wipe the slate clean here. If we want to reverse the color change, all that we need to do is increase the amount of acid in our solution. And whenever we add more acid, we are always increasing the concentration of H3O+. And again, this is a simple concentration adjustment according to Le Chatelier's principle, because if we have more H3O+, that means now our reverse rate, or rate of the reverse reaction, is actually going to increase, shifting the equilibrium in favor of producing the acid form of the indicator. And because we have more of the acid form of the indicator, that means that our solution becomes more colorless and less pink as a consequence. In the next video, we're going to look at arguably the most important concept in acid-base equilibria, how it relates to indicators, and the ramifications that this has for other applications of acids and bases.